Hello and welcome back. If you follow the channel, you know that we are trying to revive an IBM PS2 model 77 that died when we were trying to upgrade it to OS2. It became so challenging that we enlisted the help of our friend Eric Schleffer, better known as TubeTime US on Twitter, and he has been throwing everything he has at it to defeat this evil, undocumented design with proprietary chips, courtesy of IBM OmniCorp. He used a logic analyzer, reversed engineered the BIOS and made his own version for testing. He zeroed in on the proprietary I/O chip that the BIOS was failing to initialize. Fellow YouTuber IBM Museum kindly donated a dead board from which Eric took the chip. But after we replaced the chip, the board still malfunctioned from time to time, until Eric placed his magic finger on the board to heal it. There you go.
What the heck? I have no explanation for this.
It's really magic. So we are close, but we still don't know for sure what the exact intermittent failure is. The comment section went abuzz with wild theories of what could be wrong. For fun, I made a Patreon poll about what people thought it was, roughly ordered by the popularity of the comments. Of course, the most popular suggestion is always a bad cap. I still don't get this, no matter how obvious it is that this is not the failure, and even after I diagnose it, identify and replace the faulty component, and the thing is repaired, someone will always comment that I am an idiot and that it is a bad cap for sure. Well, this board is full of tantalums, the little yellow things, which do fail sometimes, though rarely, and when they do, they fail short, which makes them very easy to identify. They'll short-circuit the power rail for a whole bunch of chips and get hot. But power is of course the first thing we checked way back in episode 1, and it was okay. Plus the processor executes code, plus Eric proved that the failure is a write cycle to the I/O chip register, so a cap failure is highly unlikely. Okay, I can already see the comments, so I give up. Let's assume it's a cap. If it makes you happy, feel free to recap all of your old electronics. There was another variant on the cap conspiracy theory, one of the smaller bypass capacitors. Those would be most of the smaller surface mount caps here that are used to limit noise close to the chips. There were elaborate justifications on how such caps could get charged or discharged by the magic finger. I don't want to say never, but I bet we could remove half of these caps and the computer would still work fine. So this one does not get my vote, and most Patreons seem to agree. A bad solder joint comes next. That was actually my initial bet, and Eric's as well. Overall, the soldering quality on this board is poor. There is evidence that either not enough flux was used or that the melting temp was too low. There are beads of unmolten solder paste next to the pins. But we spent a lot of time reworking the solder joints around the suspect chips, and that did not do diddly. What about the broken trace in the PCB? That was my second best bet, and the choice of most Patreons too. Something right in the middle of the PCB, a hair crack of some kind, that gets pushed back into shape when Eric places some finger pressure on the board. Unfortunately, this does not jive well with the board bending test. Bending the board seems to do nothing. But I'm with the Patreons here, it really feels like something of that ilk. A bad pull-up pull-down resistor. It gets some votes, and actually it could explain why the board would work with a finger on it, creating some capacitive or resistive load that would temporarily replace the bad resistor. However, if that was the case, the fault would return if the finger was removed, and it does not. So there were all kinds of alternative theories of charging and discharging CMOS circuitry to try to explain the memory effect, but that does not make any sense. So I discard this one because the circuit continues to work without the finger on it. A bad lead in the I/O chip. At one point we really thought that could be the case, particularly internally to the package, because putting cold spray on the chip package seemed to repair it. But when we replaced the freaking chip, to my great surprise, the failure did not go away. How likely would it be that both chips have the same weird failure? What about tin whiskers? Oh, that one can be very real, and it was prevalent when connectors were mostly plated with tin. Tin does happen to grow whiskers, really, and I am not sure the process is that well understood. They cause almost invisible shorts in connectors. This famously happened to certain IBM 360 machines, and it turned into a maintenance nightmare. At work, our military and space customers are scared blue from this and will have us check for formation of whiskers. But this is somewhat inconsistent with our intermittent failure on a board with gold-coated traces and connectors, but we'll still drink a beer to it. A bad via, that got the second largest pile of votes. That's a variation on the broken PCB trace. Vias are the little conductive holes that go through the board and interconnect the different layers. Here we have traditional through-hole vias. They are made by plating the hole, and if the plating is too thin, when the board expands and contracts, it pistons and can break the top joint between the plated hole and the trace. Very annoying fault, very hard to detect, consistent actually with a board expansion and contraction with temperature, so consistent with our cold spray test. Definitely a contender. An out-of-spec or marginal chip input signal. Although low on the common popularity, this one was one of our other bets besides a bad PCB. A bad clock repeater or gate somewhere resulting in a degraded signal. Could work sometimes, could fail sometimes. Maybe the finger capacitive loading helps bring the signal just at the right level. But it has trouble to explain why it would stay one way or the other, even with the finger removed. Then the rest are mostly jokes. Enough already, replace it with a Core i9 and it will go way faster. So place your final bets now and let's see if Never Give Up, Never Surrender Eric can find the actual fault. Go for it. So, broken?
I think it's a broken via. See how it crackles? And on the oscilloscope, the voltage is neither 5 volts nor 0. It's in between. And depending on how much pressure I put on it with the oscilloscope probe, you can hear it crackling in and out.
Yes. It's a broken via! Bravo, Patreons! A lot of you guessed right. You can be proud of yourselves. It's definitely that pin, there's no doubt about it. How do you find that out? Just probing all the pins?
Probing all the pins one at a time.
What connection is the via?
An address line?
I don't know. So the lines all around it are address lines. But you can see here I was never able to figure out what this was. So it could be an address line, but it could be something else as well.
And it's the via where you have the little mark on
got
it.
Little stars around it.
No wonder we couldn't. Well, at least maybe on the. Now that you know exactly where it is, you will be able to see it. But I remember inspecting that region and not finding anything.
Mm-hmm.
We'll start out with the via that's next to the one that we're questionable about.
That's a good one.
0.5 ohms.
If you want me to hold the board for you.
Oh, I got it. And I'm going to move the probe over to the questionable via. But I'm going to be clever and I'm going to test at the pin of the chip.
So not to push on the via itself.
I don't want to push on it because that might
fix it.
Fix the problem. And there we go, 4 mega ohms.
Oh, it's not 0, it's 4. So it has something going through it. It's not over limit.
Yeah, there might be a little bit of flux in that via, and flux has leakage associated because it is slightly conductive.
Yeah. So do you see anything under the microscope about that via?
It's really hard to tell, but there could be a crack inside the via. Because if it's cracked all the way around...
Well, there is a crack, right? That's for sure, but I couldn't see it.
Yeah, it's really hard to see.
We would have never found it by visual inspection.
No way. I mean, even zoomed in all the way on this microscope, you can barely see that there's something. And then I guess just the pressure of the oscilloscope probe pushing down was reconnecting it.
So once you know where it is, it's of course a piece of cake to repair it by soldering a thin wire through the via. I'm already bracing for the commenters belittling us and saying they would have found this obvious of a problem in just a few minutes. But honestly, I really doubt they could repair this board except in hindsight. So Eric has been the master of the IBM PS277. It's repaired. And you've made a few additions, right?
A couple of additions. We've got a very fancy SCSI CD-ROM drive installed.
Yeah, so that was a gift from viewer Clinton Moody. Thank you very much. So that's the actual IBM SCSI disk that goes in there with the blue button.
That's right. You can see right there. That blue button that matches the blue button on the floppy disk.
So thank you so much. And with that care package also came the OS2 Warp 4.
OS2 Warp
CD.
4. And so we went and installed that with 3 floppy disks and a CD-ROM. And it was painful.
Yeah, you did that.
Installed.
You did that off camera. And actually we are probably going to get it back to OS Warp 3 because it consumes too much resources on this machine.
It has a 200 megabyte hard drive and it's almost completely full of OS2 Warp 4.
And then we had to take the old NEC multisync out of the storage so it can deal with the because by default what happens, it gets you on the wrong resolution or something.
The default setting is for an 8514 monitor which has a 43 hertz vertical refresh rate, and most modern monitors just can't handle that.
And my LCD was completely flummoxed by it. But so now we have, for a short while, OS2 Warp 4 running. And hold on a second, I have to, it's flickering like hell, so let me change to very low frame rate. So we're going to for 60 frames per second to 10 frames per second. So move your mouse slowly. And demo, it has a solitaire.
So we've got some games here. Let's try Klondike Solitaire. Oh, look at that.
Oh, they have done. Oh,
it kind of hurts the eyes a little bit, doesn't it?
It has a web browser in it?
It has a web browser. You can install Netscape Navigator, but it comes with its own thing.
Oh, we want the original thing. Let's do the...
So let's see if we can take a look here. So, connections, websites. Here we go.
Okay.
So we go websites, and then they have a list here, so we can look at business and shopping. So here's Amazon Books. Remember, this is 1996.
Okay, get Amazon
well,
Books.
Sure, let's pull up Amazon Books.
There was this newfangled thing. You can buy books on the Amazon. All right. And
server is not registered with your name server. http://www.amazon.com has been abandoned.
It's gone.
Oh no. Don't worry,
we don't know if we are in the past or in the future.
It just doesn't have an internet connection right now, so I can't find the server.
Yeah, I don't even have an internet card for the thing, but it has been abandoned. I like that. Well, we're very sorry, Jeff Bezos, but you have been abandoned. Well, that's cool, man. What a great amount of work you have put in this computer and completely revived it. I cannot thank Eric hard enough for his help and dedication to save this microchannel machine. We can now go back to our previous programming, trying to install an IBM 370 bus and tack channel card on it. But we are a bit exhausted by the proprietary PS2, so that will be for a future episode, I guess. See you then!